going to have useful information for determining the center of gravity, when you weigh the aircraft, you need to weigh it in a level flight attitude. So how do you know when an aircraft is level for weighing? You go to the type certificate data sheet to get information and specific instructions for that type of aircraft. Now, some aircraft call for putting a spirit level on a designated structural member or resting it on screws threaded into specific locations. A spirit level is just like a carpenter's level. It has a fluid-filled tube with a bubble in it. In some large aircraft, permanently attached spirit levels are located in an equipment compartment or in a wheel well, and this can give an accuracy as great as 1/8 degree. Another method is to use a plumb bob that you suspend from a designated point, such as inside the aircraft. It has a target on the floor, and when the plumb bob is directly over the target, the aircraft is level. So the FAA may ask you which method, a plumb bob and grid plate, an inclinometer, or spirit levels, generally yields the highest degree of aircraft leveling accuracy. Well, the highest degree of accuracy is found when using spirit levels. Now, why might you need to reweigh an aircraft? Well, one reason would be if the weight and balance records of the aircraft are lost, or for some reason become inaccurate. Maybe they don't correctly reflect equipment that's been added or taken out of the aircraft, or perhaps modifications that have been done to it. And if the weight and balance records are lost or inaccurate, then the only way that the correct empty weight for that aircraft can be determined is by reweighing the aircraft. You cannot look in the flight manual or the pilot's operating handbook, because that will give the weight and balance information for a typical aircraft, but that's certainly going to be different than the information for that specific airplane. Now, before you weigh an aircraft to determine the empty weight of it, you've got to take some things out of it. Remove everything from the aircraft except the items that are on the aircraft equipment list. You also want to drain all of the fuel that you can get out of it. There will be some unusable fuel left in it. And you want to fill the hydraulic reservoir if it has a hydraulic system in the aircraft. If it has any water reservoirs, you drain the water reservoirs. And if you've got a bathroom on board, you drain the lavatory tanks. But as far as the items in the aircraft, you want to get rid of everything except the ones that are on the aircraft equipment list. If people have got briefcases and all kinds of clipboards and stuff like that, all of that stuff has got to come out, because it will come out from time to time, and you only want, when you're figuring the empty weight, the stuff that's going to be staying in the airplane. Okay, when you go to find the empty weight and weigh the aircraft, the weighing points that you use, you have to indicate exactly what weighing points you used on the aircraft weighing form, because the arm values, the distances from the datum point that you are using here when you weigh it, the arm values used in the computations are based on the locations of the weighing points. So you've got to put them down on the form. Now, after locating the weighing points, when you're measuring the arms from the datum, you want to make sure that you're measuring parallel to the center line of the airplane. You do not want to introduce error by having your tape at an angle. So if you're weighing an airplane to obtain the CG, always extend the arms from the weighing points parallel to the center line of the airplane. Now, the empty weight of an aircraft is determined by subtracting the tare weight, T-A-R-E, tare weight, from the scale reading. The tare weight consists of things like chocks or supports to hold the tail up, in this case, to get a level flight attitude. Anything that sits on the scale, and therefore the scale is reading the weight of it, but is not part of the airplane. Chocks to keep the airplane from rolling off of the scales, supports to hold the plane in the proper level flight attitude, those would be considered tare weight, and you subtract those from the scale reading, because what you're after is the net weight of just the aircraft itself. And then you add the weights at each weighing point. In this case, we've got 3 weighing points. We've got a left main gear, a right main gear, and we've got the tail gear, and we're weighing the airplane at each of those points. So we would take the scale readings, subtract the tare weights, which are the chocks and the tail support, and then we would add those 3 net readings together in order to get the empty weight of the aircraft. Okay, the FAA will give you a number of problems working with the empty weight in the center of gravity, so let's talk about one of them. First of all, they'll say to you that you're going to be weighing this particular aircraft. Now, they'll give you all kinds of different aircraft, and they will not tell you exactly what airplane you're working with, but it doesn't really matter because it's just a process of going through the numbers. What they will say to you is that when you weigh the aircraft, the net combined weight at the main gears is 3,540 pounds, and the arm of the main gears is 195.5 inches, which means that from the datum line on the airplane to the main gears is 195.5 inches. That's the arm, the distance the main gears are behind the datum line. Okay, they say that the net weight at the nose gear is 2,322 pounds, and that the arm of the nose gear is 83.5 inches, meaning that it's 83.5 inches behind aft of the datum line. And they tell you that the datum line is forward of the nose of the aircraft. That makes everything easy. We don't have to worry about exactly where it is. All we know is that these are all going to be plus numbers, and it's going to be easy to work with. Now, in order to figure out the center of gravity, what we want to do is work with a formula: weight times arm equals moment. And the first thing we do with that formula is we set up a table like this with 4 columns in it. In the left column, we list the weight points that we're working with, which are the various gears. Then we list the weights at each location. Then we list the arms there, the distance aft of the datum line, and then we put the moments in. Weight times arm equals moment. They gave us the weights, they gave us the arms, we multiply in order to get the moment. Now, the first thing we know is the weight at the main gears, and the weight at the main gears was 3,540 pounds. The arm, we were told, was 195.5 inches. Let me be your calculator for you, and 3,540 pounds times 195.5 inches gives us a moment of 692,070. The moment is the force exerted in that particular location. The next thing we list is the nose gear. The nose gear, the weight was 2,322 pounds at an arm of 83.5 inches. Weight times arm equals moment, and the moment for the nose gear is 193,887. Now, the next thing we do is total the weights and total the moments. You don't total the arms. There's no such thing as a total arm. There is an average arm, which is the same as the center of gravity, but there's no such thing as a total arm. So when you total the weights, the total weights come up to 5,862 pounds. When you total the moments, the total moments come up to 885,957. What we really want, though, is the center of gravity. To get the center of gravity, if you know the moment and you know the weight, all you have to do is divide. Total moment divided by total weight will give you the average arm or the center of gravity. The total moments were 885,957. The total weight was 5,862 pounds. And when you divide that, the center of gravity, the average arm, is 151.1 inches. 151.1 inches is the center of gravity, or the average arm, the average location of the weight, if you will, on the aircraft. Okay, the FAA will give you another question, and they will ask you to determine the empty weight center of gravity, but they put some extra stuff on board the aircraft, some of which should be there and some of which has to be subtracted in order to get the empty weight and the center of gravity of the aircraft. Okay, what they say is, here you've got an aircraft. The datum is forward of the main gear. The distance from the tail gear to the main gear is 360.26 inches. The distance from the datum line to the main gear is 30.24 inches. On the right main gear, we have weight on the scale of 9,980 pounds. On the left main gear, we've got a weight on it of 9,770 pounds on that scale. And on the scale at the tail, we're showing a weight of 1,970 pounds. Now, as we look at this diagram, what they have given us is the distance from the datum line to the main gear and then from the main gear back to the tail. And in order to get the datum to the main gear, the datum to the tail, what we're going to have to do is add the distance from the datum to the main gear to the distance from the main gear back to the tail gear. And so we're going to have to add the 360.26 and add to that the 30.24, and that will give the distance all the way from the datum line back to the tail gear on the aircraft. And that comes up to 390.5, and we're going to plug that into our table in a little bit. But the FAA also says we've got some additional items in the aircraft when we weight it. And what those items are, first of all, is a lavatory water tank. We've got the lavatory water tank, and the weight in that tank is 34 pounds, and the location of the tank is plus 352, and that means 352 inches aft of the datum line. We also have hydraulic fluid. There are 22 pounds of hydraulic fluid, and it's located at -8. That means that it is in front of the datum line. It is located at -8 inches. We also have some removable ballast in the aircraft. It can be put in or taken out. It's removable, not fixed, and that is 146 pounds, and that's located at plus 380. So that's 380 inches aft of the datum line where the removable ballast is located. Now, when you're working a weight and balance question, the result of a weight being added or removed and its location relative to the datum line determines whether the moment is going to have a plus or a minus sign in front of it. For instance, if a balance computation requires that an item which is located aft of datum be removed, in that case you've got a minus weight because you're getting rid of the weight, but you have a plus arm because the item is aft of the datum, and that makes it a positive number. When you multiply a minus number by a plus number, you're going to get a minus number. So if you're removing a weight, the weight would be entered as a minus. At the arm after the datum would be a plus arm, but the result of multiplying those would be a minus moment, because just like you're getting rid of the weight out of the aircraft, if you remove an item, you are also getting rid of the leverage effect of it, which is what the moment is, and therefore you would have a minus moment when you go through the calculations. So let's set up our table again. Weight point or item, weight, arm, and moment. Weight times arm will give us the moment. Okay, the first weight point is the right gear, and on the right gear we had a weight of 9,980 pounds. The arm they gave us was 30.24 inches, and when you multiply, the moment is 301,795.2. The second item is the left gear. The weight they gave us on the left gear was 9,770 pounds. The arm is the same as for the right gear. They're the same distance aft of datum, 30.24. Multiply weight times arm, and the moment is 295,444.8. Then we've got the tail gear. The tail gear, we were told the weight there is 1,970 pounds. The arm of the tail gear is 390.50 because we took the distance from the datum line to the main gear and then the distance from the main gear back to the tail and added them together to get that 390.50. Multiply and the moment is 769,285. Now, as far as the hydraulic fluid is concerned, hydraulic fluid belongs in the airplane. It is part of the empty weight. So we don't do anything at all as far as the hydraulic fluid is concerned. It was included when the airplane was weighed. It should be included when the airplane is weighed. But what we do have to remove is the lavatory water. We got to get rid of that H2O, the lavatory water, because it doesn't belong. There was 34 pounds of it, and we're getting rid of it. So under weight, we put a minus 34. The location of the lavatory water tank is 352 inches aft of datum. It's aft of datum, so it's a positive number. We put it in there as 352. Weight times arm equals moment. We get a moment of a minus 11,968, and it's a minus moment for the lavatory water because we're getting rid of the weight, and when you get rid of the weight, you get rid of the effect of that weight, and that's what the moment is. We also have to get rid of the removable ballast. Because it is removable, it's not included in the empty weight of the aircraft, and therefore we put in a minus 146 pounds for the removable ballast. The arm of it is 380 inches. Weight times arm equals moment. The moment for the removable ballast is a minus 55,480. And then what we do is we total the weights and we total the moments. The total weights are 21,540 pounds. The total moments are 1,299,077 for the moments. Okay, we've got the weight and we've got the moment, but what we really want to have is the center of gravity. Center of gravity, take the total moment, divide it by the total weight, and that gives you the average location of the weight, the average arm or center of gravity, and when you divide the total moment by the total weight, you get a center of gravity in this particular case of 60.31 inches. 60.31 inches. Remember, hydraulic fluid belongs in the airplane. Do not get rid of it. But water in a lavatory tank or removable ballast are not part of the empty weight and do have to be subtracted out. Okay, they'll give you another question that looks like this. They'll say to you, you've got an airplane, and rather than giving you the weights on each of the wheels, they'll say to you that the total empty weight as weighed is 5,862 pounds, and the total moment of the airplane with the empty weight is 885,957. On board the aircraft, when it was weighed, are a couple of additional items. First of all, alcohol. 20 pounds of alcohol at a location of plus 84 inches. Also hydraulic fluid. On the hydraulic fluid, you had 23 pounds on board at a location of plus 101 inches. The pluses simply mean that it's located after the datum line as opposed to in front of it. And the question is, what is the center of gravity, the empty weight center of gravity of the aircraft? So we set up the table. The weight point or items, the weight, the arm, the moment. Weight times arm equals moment. And the first thing we put in there is the empty weight of the aircraft itself. The weight is 5,862 pounds. The moment is 885,957. And the arm of the airplane at that point is 151.14. Now, the arm was not given to us. The arm we calculated because if you have the moment and you have the weight, you can divide and you can come up with the arm. And we did it just to fill in the table. Okay, alcohol. Is alcohol included in the empty weight of the aircraft? No, it's not. So the alcohol has to come off. There were 20 pounds of it, so under weight you put a minus 20. It was located at 84 inches, so under arm you put 84. Weight times arm equals moment, and you get a minus 1,680 for the moment. You're removing the alcohol, so you remove both the weight of the alcohol and also the influence, the effect of it, the moment of it, from the calculations. Now, hydraulic fluid. Does hydraulic fluid belong in the empty weight? Yes, it does, and therefore you don't do anything about it. It was in there when the aircraft was weighed. It's supposed to be in there in the empty weight, so you don't have to worry about doing anything with the hydraulic fluid. The next thing you do is you total the weight and you total the moment. The total weight is 5,842. The total moment is 884,277. And what we want to know is the empty weight center of gravity. So we take our formula. Total moment divided by total weight will give us the center of gravity, and you take the total moment, 884,277, divide it by the total weight, 5,842, and you get a new center of gravity for the empty weight of 151.365 inches. 151.365 inches. See? Nothing to it. And really there isn't, as long as you remember to set up the table, because it's important to keep the problem organized. Otherwise you end up with numbers all over your scratch paper and you don't really remember after a while exactly what the numbers mean. Here the FAA will give you another question having to do with determining the empty weight after an engine change. And they'll say to you that you've got an aircraft where you took out a B model engine that weighed 175 pounds and you installed instead a D model engine that weighed 185 pounds. The datum line is located right about here, roughly in this diagram, the leading edge of the wing, because of the way the numbers, the stations are given to you. They say to you that the station of the engine is a minus 62 inches. Well, if it's a minus number, it has to be in front of the datum line, which means the datum line needs to be about the leading edge of the wing and the engine's out in front of it. And they also tell you that the previous empty weight center of gravity is 13.48 inches and that the previous empty weight, this is before the engine change, was 998 pounds, and what they want to know is what is the new empty weight center of gravity when you get done with this engine change. So you set up the table, item, weight, arm, and moment, and then start filling in the numbers. And the first thing is the original empty weight of the aircraft. It weighed 998 pounds. The arm was 13.48 inches. Weight times arm equals moment, and the original moment was 13,453.04. Now you're going to take out the B model engine. So under weight you put a minus 175 pounds because you're getting rid of it. Now the arm of that B model engine was a minus 62 inches. That minus is because it's in front of the datum line. And that's fine, no problem. Put it in as a minus arm. But the thing that happens is when you multiply a minus weight times a minus arm, this time, instead of getting a minus moment, you get a plus moment. And you get a plus moment of 10,850 because a minus number multiplied by a minus number will give you a positive number. Okay, you took the B model engine out. Now you put the D model engine in. You install the D model engine. It weighs 185 pounds, so you put under weight a plus 185. The location of it is an arm of minus 62 inches, so under arm you put a minus 62. Weight times arm equals moment, and you get a moment of 11,470, and that is a minus moment because you had a minus arm. In this case, it's not a minus weight that makes it a minus moment, but the arm has a minus number and a negative number, and therefore you end up with a negative number for the moment. And then you simply total the weight and total the moment. The total weight is 1,008 pounds. The total moment is 12,833.04 0.04. And in order to get the new center of gravity, we simply use our formula of dividing the total moment by the total weight to get the center of gravity. And when you divide the total moment, 12,833.04, by the weight of 1,008 pounds, the new center of gravity for the empty aircraft after the engine change is 12.73 inches. 12.73 inches. Okay, the FAA will ask you another question where they don't change the engine, but they do a lot of other changes on the aircraft. And what they say is the original empty weight is 2,886 pounds. The original moment of the empty aircraft is 101,673.78. What you do is you take 2 passenger seats out. The passenger seats weigh 15 pounds each, and they're located at plus 71. That means 71 inches aft of datum. You install a cabinet that weighs 97 pounds that's located at 71 inches. You install a seat and a safety belt that weighs 20 pounds, and you put it in at 71 inches. And you install radio equipment, and that radio equipment weighs 30 pounds, and it's located at 94 inches. And the question is, what is the new empty weight center of gravity? Okay, so you simply set up the table, item, weight, arm, and moment. And the empty weight of the aircraft is 2,886 pounds. The moment was given as 101,673.78. To get the original arm, the center of gravity, you divide. If you've got the weight and you've got the moment, you divide the moment by the weight, and you get the arm on the empty weight of the aircraft. And it was 35.23 inches to begin with. Okay, you take out 2 seats. The 2 seats weighed 15 pounds each, but that's a total of 2 times 15, or 30 pounds you're getting rid of, and it's a minus weight because you're taking it out of the aircraft. It's located at 71 inches. Minus 30 times plus 71 gives you a minus moment of 2,130 for the seats you removed from the aircraft. Now you install a cabinet. The cabinet weighs 97 pounds, so under weight you put 97 pounds, under arm you put 71 inches. Weight times arm equals moment, and the moment for the cabinet you installed is 6,887. You also installed a seat at the same location, but this seat weighed 20 pounds, not 15. 20 pounds under weight times 71 inches under arm gives you a moment for the seat you installed of 1,420. You also put in a radio, 30 pounds worth of radio at location 94. Weight times arm gives you a moment of plus 2,820 for the arm on the radio that you put in. And then you total the weights and the moments. The total weights come up to 3,003 pounds. The total moments come up to 110,670.78. Okay, what we want to do now is we want to determine the center of gravity. We want to figure out where the center of gravity is located. Total moment divided by total weight will give us the center of gravity. 110,670.78 divided by 3,003 gives the new center of gravity of 36.85 inches. Now, most of the problems like this will stop right there, but not all of them will. In some cases, the FAA will say, what is the change from the old center of gravity? How much has the center of gravity moved, and which direction has it moved? The new center of gravity is 36.85 inches. The old center of gravity was 35.23 inches. When you subtract the two, the difference, the change, is 1.62 inches. 1.62 inches. Now, the new center of gravity is further aft of datum than the old one is because it's a bigger number. It's 36 inches and some instead of 35 and some. So the center of gravity has moved rearward. It's moved towards the aft position in the aircraft when you made the change. So the new center of gravity is 1.62 inches aft of the old center of gravity. Now let's talk about the theory of weight and balance. The theory of weight and balance is the same theory as of a lever that is in balance, in equilibrium, when it's resting on a fulcrum in a level position. This, in essence, is what we want the airplane to do. The concept we're working with on the airplane, the center of gravity is the same as the fulcrum. It's the balance point here on our lever. Now, let's talk about the concept of lever arm. The distance that any object is from that fulcrum is called the lever arm. What we've been working with in general has been just the arm, the distance that something is from the datum line, and the datum line has been up at the nose of the airplane. But let's assume that you put a fulcrum at the center of gravity of the aircraft and then measured from that instead of measuring from the datum line. What you would have then is a lever arm, because this is the distance behind the balance point, or in front of the balance point, the point that the aircraft or this lever is rotating about. Center of gravity is what the aircraft rotates about, and so if you measure from there instead of from the datum line, you get the lever arm of a particular item. And the FAA will give you some questions that require you to work with that. For instance, they will say to you that you have put 2 boxes in an airplane. We're going to use this lever to illustrate it because it works a little bit better. One of the boxes weighs 10 pounds and is located 4 feet aft of the center of gravity. Another box weighs 5 pounds and is located 2 feet aft of the center of gravity. You've got another box. You've got a 20-pound box, and you're going to put it in front of the center of gravity. And the issue is how far forward of the center of gravity, the balance point, the fulcrum, if you will, how far forward of the center of gravity can that 20-pound box be placed so that the center of gravity does not change. In other words, you started off with a lever in balance, an airplane in balance. You added 2 boxes behind the center of gravity. You're going to put a third one in front of it, and the issue is how far forward of the center of gravity does that box need to be in order to balance these other 2 weights. Okay, simply set up a table. And in this particular case, when you set up the table, the columns are item, weight, lever arm, and moment. Lever arm, because we're not measuring from the datum line, we don't even know where that is in this particular problem. What we're doing is we're measuring from the center of gravity, which is the same as that fulcrum that we looked at. Okay, so we start adding the items in, and first of all, we've got box 1, which weighed 10 pounds, had a lever arm of 4 feet, and 10 times 4 gives us a moment of 40. Then we add in box 2, which weighed 5 pounds, had a lever arm of 2 feet, and that gives us a moment of 10. And then you total the moments. We're not really interested in the weights here. All we're interested in how much force do we have to counterbalance. And the total moments added aft, to the aft of the CG, to the aft of the fulcrum, are moments of 50. Now, in order for this aircraft to be in balance, when we put the third box in, what we have to do is we have to balance those moments. So we're going to have minus 50 moments. That means an effect of 50 forward of the center of gravity. We know we're going to put 20 pounds forward. What we don't know is how far forward we have to put it. Well, remember that weight times arm equals moment, and moment divided by weight will give you the arm. It's the center of gravity if you're working with a whole airplane, or the arm if you're working with an individual item. And so we have a moment of 50, we have a weight of 20, and when we divide 50 by 20, we have to put that box 2.5 feet forward of the center of gravity. It's 2.5 feet forward in order for that aircraft to be in balance when that third box goes into it. Now, the FAA will ask you a question about putting a ballast weight in an aircraft to bring the center of gravity within the center of gravity range. We've already said that there's a certain allowable movement on the center of gravity that it's allowed to move within, and you can't exceed that safely. the FAA will give you the following information. They'll say you've got a loaded aircraft that weighs 4,954 pounds. They'll tell you that as currently loaded, the center of gravity on the aircraft is located at 30.5 inches, 30.5 inches aft of the datum line. They'll tell you that the allowable CG range on the aircraft is 32 inches to 42.1 inches. You can see already that you've got a problem, because the center of gravity as the aircraft is loaded is forward of the allowable center of gravity range. It's outside the range to the forward of the aircraft. Now, to get the center of gravity back in range, what you're going to do is put some ballast in the back of the aircraft, and the arm on the ballast is 162 inches, which means 162 inches aft of the datum line. What they're going to say to you is, after giving you these numbers, how much weight of ballast do you put at this location in order to move the center of gravity within the allowable range? And that means that you need to have the center of gravity move from 30.5 inches to exactly 32 inches, because when they ask you what is the minimum weight that you have to put in the ballast location, what they're asking is what is the minimum weight needed to bring the CG to where it's exactly legal. Not in the center of the range, but to where it's exactly legal, and exactly legal would be a position of 32 inches. Now, the way that you think about this is that the weight, the ballast that's added, causes a moment change in the whole aircraft that's equal to the moment change caused by adding the weight. So what you do is you put a fulcrum where you want the airplane to be in balance when you're done. You put it where you want the airplane to be in balance when you're done, which in this case is the forward limit of the allowable center of gravity range. And from that fulcrum, you compute lever arms for the items that we're working with. The center of gravity is 30.5 inches aft of datum. The forward limit of the center of gravity range is 32 inches aft of datum. From 32 to 30.5, the difference between those is 1.5 inches. So we've got a lever arm here of 1.5 inches that we have to move the center of gravity. Now, from where we want the airplane to be in balance when we're done, which is 32 inches, back to the location of the ballast that we're going to put in the plane is a distance of 130 inches. And we get that by taking the arm of the ballast, which is 162 inches aft of the datum line, and subtracting from 162 inches the forward location of the foremost limit of the center of gravity, which is 32 inches. 162 minus 32 gives you a lever arm of 130 inches for the ballast weight that we're going to put in there. And then all we have to do is work through our same table, but using the lever arm rather than the original arm, the distance from the datum line. So when we put in our table, first of all, we put the CG shift that's needed. The weight of the aircraft is 4,954 pounds. That goes under weight. The lever arm is a minus 1.5 inches because the original center of gravity is 1.5 inches in front of where it's allowed to be. Weight times lever arm gives us the moment, and that gives us a minus moment of 7,431. What we've got here is we've got moments of 7,431 in front of the allowable CG limit that we have to counteract, that we have to counterbalance. So to balance those moments, we need positive moments of the same amount, 7,431. Okay, we've got the positive moments of 7,431 that we need. We know that the lever arm on the ballast is 130 inches. And all we have to do then is divide. This time we're dividing in order to come up with the weight. And here's what it's going to look for. We take the moment, which is 7,431, and we divide it by the arm. The lever arm was 130 inches, and the ballast weight we have to come up with then, have to put in the aircraft, is 57.16 pounds. 57.16 pounds. Remember, we said if you've got any two numbers, you can always get the third in our weight and balance formula of weight times arm equals moment. In this case, we got the moment in the arm, and it's the weight we need to find out, and we need 57.16 pounds of ballast in order to bring the center of gravity back to the leading edge, to the forward limit of the allowable center of gravity range. Now let's talk some more about that center of gravity range, that empty weight center of gravity range. The empty weight center of gravity range is the allowable range of travel within the center of gravity limits. If the empty weight CG of an airplane falls within these limits, then it is not necessary to calculate extremes on the center of gravity, because as long as the empty weight CG of an airplane falls within the empty weight CG range, it's not possible to load the aircraft so that it's going to get out of the CG limits as long as standard loading arrangements are used. But there are some aircraft where the empty weight center of gravity is outside the center of gravity limits, empty weight center of gravity limits, and you have to calculate center of gravity extremes to see whether or not that plane is going to be within center of gravity when it actually is flown with people and so on in the aircraft. And when you do that, you may end up with a situation where you have to put some ballast into the aircraft. So they're going to ask you about the weight and balance